Hey guys, it's Udbhav from Team 19343. This video is a continuation of my FTC programming course in Android Studio. Today's video will be on finite state machines. This video will include what finite state machines are, how they work, and their function in FTC with real examples from our last year's bot. It will also include how to mesh two finite state machines together, as well as introducing sensors to elicit actions using the same. Just as a disclaimer, I won't be going step by step on coding every line of FSM, as it is generally a very long program which varies significantly with your chosen variable names and actions you want to elicit from the bot. It will take some time to learn and implement into your bot, so be prepared to spend some time getting it right. However, once you code the FSM, it will make controlling the bot extremely efficient and easy for the drivers to learn, which is what the programmers do. Not just make the bot move, but make it move with as little effort as possible. First, let's understand what a finite state machine is. It is, well, exactly what the name suggests, a system with a finite number of states. That is, in one state at a time and can be transitioned to a different state when something occurs in the system. In the context of FTC coding, it is useful for running multiple tasks at the same time, or triggering a series of actions based on a certain input. So, for example, a sensory input. FSM is very useful as it allows tasks to be completed based on another's execution in a non-linear fashion. An example of FSM is a turnstile machine in subways or metros. There are two states of the turnstile, locked and unlocked. There are two possible inputs that can change the state of the turnstile, inserting a coin and pushing the turnstile. If no coin is inserted and the turnstile is pushed, there will be no change in the state, as the turnstile remains locked. However, if a coin is inserted, then the state of the turnstile changes to unlock, and with the addition of further coins input does not having any effect on the state of the turnstile. When someone pushes the turnstile, the state is once again shifted from unlocked to locked. This is a very simple example of a finite state machine. Let's move on to a more complex FSM, a sample code I created for last year's game, Center Stage. I wanted to automate the outtake portion of our bot by beginning a series of actions based on a sensory input from the intake box, in which the pixels sat. Once a pixel has been detected in the intake chassis, the outtake mechanism will descend and pick up the pixels. From there, the driver can click the A button to bring the pixel out, and can utilize the separate unlock functions to drop the pixels. Pressing the A button will reset the FSM, bringing the whole series of action full circle. Essentially, I use this FSM to automate the function of our outtake, using pretty much only one gamepad input. The use of the sensor further automates the process, making the robot move smoothly and with little effort from the drivers. Here is our code. Take a look at it. Initialization. And here's what the actual FSM will look like. So up here, we create them. Our outtake position, our register positions. So here, our public enum stands for basically an FSM. So I have two FSMs in it, outtake sensor and outtake sensor 2. And here are our switches and our cases. So as you can see, I'm setting a certain distance to our sensor, our distance sensor. So that's what exactly triggers the full FSM or the finite state machine. All right, so to create a finite state machine, we need to give a public enum and include the states below. Remember to relevantly name your states to give yourself an easier time when we code components under the same. We also need to include these two lines to set the initial state, and as well as to set the outtake sensor timer to a new elapsed time. Finally, if you need to, code in a double for timer in case you need some break time to give your components time to move. And obviously, remember to initialize your components and give the necessary reverse commands. Now, let's move on to the actual commands we can give to the FSM. First of all, to call the finite state machine, give the switch command and the name of the FSM. As you can see, for each case, I've given an if statement. One, to give the initialized double as timer, which was for 0.5 seconds, which allows the component's time to move. So for example, the arm went from position 0.85 to 0.78. And also, to have the case down to pick, or my first default, to start on the input of the distance sensor when it is less than 30 centimeters. Underneath the cases, we need to give the component actions. This is where the basic teleop code comes in, as you already have all the values and powers for your components ready to insert into the cases. At the end of each case, we reset the outtake timer and instruct the finite state machine on what is the next step of the operation, or in other words, which case is next. Finally, we give the break command and code the next case. Here's the entire code. Now, you may have noticed that I have two finite state machines running, each one based on a state from the last. You may think, why not just use one finite state machine program? You see, sometimes when we involve sensors such as the distance sensor, if we simply clump all the states into the same FSM, we end up calling the FSM to continuously loop, making it unusable. As the default state somewhat coincides with the distance sensor's vision, this is the result. By creating a second FSM, we break this loop, allowing the entire program to function as a whole while still maintaining the automation of the outtake process. That wraps up today's lesson on finite state machines and their application in FTC programming. We covered the basics of what an FSM is, explored real-world examples, and discussed how FSMs can be applied to automate and streamline functions in your own robot, as shown with the outtake mechanism example. Remember, programming FSMs takes time and practice, so don't be discouraged if you encounter challenges while implementing your own. This is Udbhav from Team 19343, signing off.